is calling you. The universe is calling me. 'I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. Fields and forms, math and voids. It all sings with one voice. It's boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Well, hello everybody. Welcome to SkyTour live stream. How are you guys doing? I am Mark D'Antonio, and as always, let me just take care of this little bit of housekeeping, and I'll bring Daryl in here in just a second. There we are, housekeeping done. And with us, of course, as always, is Daryl Mason. Hello, Daryl.
Hello, Mark. Hello, everybody.
So we are here. I actually had to do some crazy maneuvers a little while ago because the telescope started spinning madly again, but I managed to shut everything down, start it over, and it works fine. Hey, you know, I don't understand it. Sometimes this happens after the rain, and we had some rain out there, and we ended up having some issues, but as you can see, we're doing okay right now. I haven't done a focus run yet. Let's go see how close we are, just out of curiosity. Well, as you can see, the trapezium stars in the middle here are not focused, so we will do a focus run. It's looking at the entire frame, not just this. All right, so we're out of focus now. So what we do is we'll pick this right here. And you see it's using stars outside this field as well. And we'll now tell it to go do a focus run. So how is everybody? How you doing? Welcome to SkyTour Livestream for today, this beautiful leap year day. Oh, that's why the telescope was screwing up. It was leap year.
Uh-huh.
Holy cow. It was a leap year issue. Wow.
Leap day.
Yeah. Yeah. Holy cow. I just realized that that's probably what it was. So there we are. So that's most likely what happened. The focus run's going to bring into focus and then bring it out of focus again and then find that lowest point in the curve. You can see the curve building right there. Okay, right here. You see it. All right. Yeah, by restarting the observatory, I had everything was fixed. So that's kind of weird. All right. So let me just back out a little bit here. That's what it was. I couldn't believe it. How about that? I want to say hi to you guys, you early birds, okay? Fantasy, Fantasy's here, and I see you, Fantasy. Dagger's with us. Hey, Dagger, good to see you. Tim F. Gabrielle, hi, Gabrielle. How are you? Thank you for the hearts and the thumbs up. And we have Michael Hedrick with us. Michael Hedrick always has wonderful questions for us. I'm going to hit the best focus now, so we're going to take these stars and bring them back out of focus and then into focus again. And like magic, you will see them pop into focus. Da boom. Here we are. Really nice. Now you see all four of these trapezium stars that we're looking at here. There's actually more in there than four. But that's what we're seeing right now. And then I can actually blow it up really bright. So you see, when you want to see other details, what you end up doing is losing kind of the inside. You can still see it just a little bit.
I see Barney belching.
Hey, Homer, look, a peanut. Remember that?
Don't you see that?
No.
I mean, forget Bill Murray. I see Barney from The Simpsons belching.
Is Barney here? Or is Barney here?
The dark bay, the fish's mouth it's sometimes called, that's his mouth. His lips above and below, and his lips are flapping like he does when he belches. His nose is just above the mouth, right there, that point.
Yeah.
And then that's his eye to the upper right of the point of the nose.
Right here.
That dark patch, yes. And then that's his chin down under the mouth.
Okay. So
He's
it's
got a
like...
receding chin.
Hey, Homer.
Exactly.
All right. Oh, wow.
You see Barney?
I see a figure, yes.
All right.
Oh, yeah, that's funny. That is so funny. Thank you, Gabrielle. I'm glad that it's beyond glorious. This is fantastic. Now, this noise that we see is from the sensor, of course, but when you actually zoom out, it really looks nice, you know, and this is just the raw view. We're looking at a raw view right here. We're not, right now, we're not doing anything. We're not taking a picture. We're just looking at the screen and checking it out, you know. But I will say that, as Fantasy says, this is everybody's favorite, you know. But there's a lesser known but equally intense region just above it. And what I want to do is just take you up there just real quick. Again, staying in live mode. We're just zipping the telescope around the sky right now. If you really look carefully, you'll see it moving. It's very, very subtle, though, because we're only going up a short distance. All right, and then we get up to here. And this is interesting, this region right here. Because this is a location where there's another set of nebulae. I don't know how many of you actually saw my post today, but I didn't stream last night. But in between cloud banks, I actually opened up and I did this mosaic of this entire region really deep mosaic. Each image was 45 seconds, which is deep for us, at a gain of 250. Again, this is the exposure time over here. All right, right now it's on 1,000 milliseconds, which is 1 second. And then the gain right now is at 250. Well, I had the gain at 250, but this number went to 45,000 milliseconds. And every 45 seconds, an image would come in and I'd stack. Okay, because Daryl wasn't here. Nobody was with me. I was just doing it myself because I needed that fix. And so I ended up creating this set of images. I did one here, did one down below, and I just did this whole mosaic of the entire region. And it's on my Facebook page. It's on the SkyTour live stream on Facebook page. It's not on SkyTourLive.org at the moment, but it will be eventually. But that really was just glorious. It just looks so incredible. You can kind of see the subtlety here. And just for fun, what I'll show you is I'm going to do a 25-second shot. 25S means 25 seconds. All right. And then we'll come out down here. And when we come down here, down below, on the right here, you'll see a yellow bar appear. That is the frame. And so I'll start the live stack. And the live stack that you see here, we take an image, take a second image, align it with the first, star to star, and then stack on top. Keep doing that and stack an image sandwich. And the more we do, the clearer it gets, the better detail we can see. And it is called stacking. So this image here, if it comes in, and I'll tell you why I say if it comes in, and it did, okay, is because, so there you see, now that doesn't look like much right now, and that's because we're going to color correct it first. We're going to line up all our curves. See the curves here, the red, green, and blue curves have to align with each other. If they're off, then you can get something that looks like this. I'll move the red up, all right? You see how the red curve drifts? There's too much red now in the signal. So if I just align all the curves, line them all up with each other, now this is the actual color, and then these dashed lines are to the right side of the data. Here's the peak of the data right here. So what we want to do is move these over so we can intercept more of the data, and look at that on the screen. You see more data, right? Let's see what it wants to do. This will do that for me. Okay. And that's pretty fascinating. It actually moved almost to the same place. So here you see this nebula here. This is called the Running Man Nebula. Now this one I see, Daryl. I see the Running Man. It's a guy here. Okay, there's his legs right here, and he's running really fast. That's why it's called the Running Man Nebula. He's got his arms outstretched. Really interesting. Hey, old school. Yeah. How you doing? All right.
I always think Arnold Schwarzenegger when I see this.
That's right.
Because that dumb movie.
Stick around. What happened to him? He got all burned up. So, yeah. So, again, right now we've got 4 images stacked right here. You can see, right? And you see me looking to the left and to the right. There's a gigantic panorama monitor in front of me. And I have the observatory feed over here. And I have the broadcast feed to the right. So sometimes I'll be looking to the left over here, and sometimes I'll be looking to the right. But I'm still looking at the same image up here that you're looking at, okay? So when I point to this star, I could be looking there or there and still be pointing to it, okay? Hey, Marco. Nice to see you. Oh, yeah. So what's happening now is I've got a setting here that I'm using, and what this is called the full width half maximum setting. What's happening is we're lowering the, this is a indicator here. See that dashed line lowering and raising, and this is basically a study of the roundness of the stars. The smaller the number, the rounder the stars will be. If I turn it off, these stars could end up being quite significant dashes by wind or some other things. Obviously, the telescope itself is guiding on the stars, so it's following them. But because I have this number so high right now, we have a subtle vertical set of dashes, okay? I actually have a way to combat that. What I'll do is I'm going to go in here and do that, because I am going to change my numbers to make that work better. All right, do that. And then I will come in here. I just changed the east-west, left-right motion. And now I'll change this declination motion. And I'll set it to 23. So that means that it's going to make corrections to manage this problem that we have if the thing is not quite aligned. All right. And we'll see these numbers drop down over time, depending on where we are. If we're up in high northern latitudes, this number can get down as low as 5. When we're on the horizon and the celestial equator, then these numbers will end up being anywhere between 7 and 11. And in there, you can still get round stars. But ideally, you want to stay under 10, under 9. All right, so 9.78 is about the limit. So if I drop this down, okay, and I say, okay, we're going to leave it right there at 10. Let me take it underneath. Let's go to 9.78, this exact number. The next one that comes in, if it's higher, it might make a slightly elongated star. Again, because of the guiding error and the wind and the other variables that are out of our control, it won't accept the frame. See, 9.1, it accepted it because it was acceptable. But notice how much better the image looks now. Remember, it looked kind of grainy and rough. Now it's starting to look a lot smoother, isn't it? Well, that smoothness is directly due to the fact that we have stacked a number of these images on top in that image sandwich. That image sandwich takes the noise, which is random stuff you see. And if I zoom in, you'll still see some. Okay, let's see. All right, see that? There's noise in here, right? I can actually get rid of a lot of that noise, okay, with this right here. Watch this. Watch the screen. See all those colors? Bam. Look at that. They all go away. I remove that, and this is going to increase the resolution of what we can see all the more. So now, look at that nebula. Now you see the running man with his arms outstretched and his legs, his head. He's very, very clear now. All right? And you also see this dark dust cloud. This dark dust cloud is a remnant from supernovae, from the outer shell ejection, from super giant stars, red supergiant stars in the late stages of their life. They're at a point where stars will go to a red giant phase, 2 times in their life, many times. And high mass stars, they'll go up to red giants when they start running out of hydrogen fusion fuel, which hydrogen they make into helium. And finally, as that star's core contracts because it's running out of hydrogen and gravity starts squeezing it in, the outer radiation gets higher, and so the star bloats into a red giant. That's the first time it becomes a red giant. When that happens, that temperature inside that core is getting higher and higher and higher and higher until finally it reaches another point. And that point is high enough to start fusing helium into carbon. All right? And when that happens, that star then begins to shrink down just a little bit. And then when it runs out of helium, it bloats again, sometimes even bigger. And that phase of its life is called the AGB phase, or the asymptotic giant branch phase. Nothing you have to remember. Just remember that at that point, when the star is really, really big as a red supergiant, those outer layers of the star can be so far away from the heat-generating core, the fusion operating core, that it's relatively cool. An example, if you put Betelgeuse in Orion, where our sun is, the outer extent of Betelgeuse would reach all the way to the planet Jupiter. Wow. And what that means, in fact, is that if it's out as far as Jupiter, it means that it's relatively cool. Even though it's part of a star, it's relatively cool. Cool enough to get molecules. And many times in the outer atmospheres of stars, you're going to get many different kinds of molecules. Among them, silicon and carbon molecules. Carbon loves to bond with itself. You have a carbon-carbon molecule, 2 molecules of carbon. Carbon is the 4th most abundant element in the universe. I've said it a million times. And so therefore, you can expect that if there's going to be life in the universe, it'll probably be based on carbon. You know, and I guess that makes me, as I've said to many people, I'm a carbon bigot, I guess. But that's true. Oofy's with us. Hello, Oofy. How you doing? It's good to see you. Did you see my post on Asteroid Miners Guild? I think you saw that. Cindy Murphy, hello.
Guilty asteroid miners? What are they guilty of?
No, I didn't say guilty. Guild, Gyld.
Oh, okay.
Asteroid Miners Guild.
Roger. I get you now.
Yeah. All right. So this is pretty cool, and so now, again, this here I was only showing it to you briefly, but you know I will get to I'll get to show you a few other things here in just a second. Another little housekeeping thing that I'm doing right now. Let's try this.
Reminds me of Brian Keith in The Mountain Men with Charlton Heston. Lost? I ain't never been lost. I've been damn confused for a month or two, but I ain't never been lost.
I remember that. That was a good movie. You know?
Uh-huh.
Okay. All right.
I think the only thing I'd ever seen Brian Keith in was Green Acres, so it was quite a change for me.
Green Acres, really?
Oh, no.
You're not talking about Green Acres.
What was a dumb TV show? Two little kids, and
yeah, I remember that.
he was a very urbane fella, and the butler was the big old dark-haired guy with a beard.
Yeah,
That was Brian Keith, wasn't it?
I believe it was. I can't remember the show. I'm sure someone in chat will remember the show. Boy, I can just almost remember it.
Who was in Green Acres? And Eddie. Holy cow!
Eddie Arnold? No. Oh, Green Acres. That was Edward Arnold, right, as Oliver, and Zsa Gabor or Eva Gabor. I can't remember.
Eva.
Yeah, Oliver. Donald Kunzer's here. Hey, Donald. Did someone say movie trivia? So, yeah, Donald Kunzer, Eddie Arnold, and Zsa Gabor. Thank you. Yeah. Well, Eva Gabor. Sorry. But you know what? While we're waiting for this to come in, there is Donald Kunzer. If you're into movie trivia, Brian Keith was in a show with two little kids. It was a series, and I can't remember the name of it. Neither can Daryl. We're both trying to remember the name of the series. I do remember this. I do remember that.
Yeah, the boy and a girl. They were brother and sister.
And one of the
orphans,
I think the girl was named Jody. I think Buffy and Jody. So Jody was the boy, Buffy was the girl. Remember that?
Yes.
So, who were they? Family Affair. Donald Kunzer. He strikes gold.
Who was the butler?
Oh, that was that.
The big portly guy, dark hair and a dark
famous
beard.
guy. A famous guy. I remember him.
Yeah.
It was like I'm going to say a name that's wrong. Peter Ustinov or something. That's not him. Mr. French was the name of the butler, but who played his? Yes, that's right. Okay, let's back out of this and see what it looks like now. Look at that.
Sebastian Cabot.
That's right. Well
Thank
done.
you, Donald.
Donald's the man. Donald is the man. All right. So here, check this out, guys. So now what you're seeing is the Running Man with the attendant other nebula that's around it. And let's see if we can bring out a little more detail here. First things first, let me sharpen this stuff up a little bit for you, okay? So bring the music down a little bit. Let's add an unsharp mask. Now watch this. Magic has just occurred. Look how much sharper everything is. All right, and now we'll go back to the histogram. And the histogram is just the data that the sensor sees, right? And what we're seeing is everything to the right of this first line. And this is our data right here, the average amount of data that we're picking off. So everything under this curve is what we're actually sampling right now. So if I bring this midline in, you'll see that it's going to get a little bit brighter because that curve's rising up. See it? And now, as I bring it up, watch the screen, right? This stuff here is starting to get a little bit brighter. See that? And now, this is the black level. If I move it too far to the left, then we just get noise and it gets too bright. All right, like that. But if I move it to the right and I start climbing that curve, as long as I don't get just over the top of the curve, if I stay right about here, right about there. Now we see all the detail. Look at that. And we haven't lost any data. We have all the data. This is what's called an elementary image processing. All right. So here is the Running Man. Here is this other beautiful nebula out here that's part of it. And look at they look like clouds because they are. This light you're seeing here is literally reflected light from down below in the Orion Nebula. However, this blue light is also caused by this dust. Now, how does that happen? Well, inside here there are bright stars, and the dust are very small grains of dust. Okay, very, very tiny dust grains. Well, these tiny dust grains are extremely good at scattering blue light. That is to say, high, short wavelength, high frequency light. And blue is high frequency. So when you look at high frequency light in our atmosphere coming in from the sun, you'll notice that the air molecules are doing to the light what the dust particles are doing to the starlight here. Notice this color blue? You've seen it before. It's the same blue as in our sky. That's because our sky is turned blue for the same reason. The dust and the molecules in our atmosphere are very good at scattering the very, very high frequency light, or the blue light. So that is why the sky is blue, and why it's blue everywhere we look, because everywhere we look, the molecules are scattering light during the day. And in these nebulae, you're seeing it from many light years away. We're seeing this from about 1,500 light years away, which technically means we're seeing it 1,500 years ago. And so at that time, the light was being scattered, the dust was scattering the light we see here. Same here, same here. So you see, we've got lots of really interesting things going on here. And these are obviously satellites here. When they go on a diagonal, they're probably Starlink. Notice we have one that went here, we have one that went here, we have one that went there. Okay, these are likely Starlink satellites. They cross in a pattern like this. They don't go north-south or east-west directly. They go on diagonals to get best coverage that way.
Ufiatori has a question of you.
I see. Ufi says, can you easily sample the RGB value of what blue you are talking about? I'd like to compare to what we're seeing on our monitor. It's this area right here. I don't have access to the RGB values in this application. I'd have to go into Photoshop with this and then tell you exactly what I'm looking at for RGB values. But you're looking at this blue right here.
I mean, it's literally sky blue.
Yeah, but Ufi wants the R, G, and the B settings, and yeah. I understand that.
Some might call it cerulean blue.
Yeah. Well, there's artists that do, that's for sure. Okay. So that is really cool. So if we zoom out, you actually see better what this looks like, this region. Now you can tell that this is kind of like a cocoon of material in here. But there's something else magical that's happening in here. And yes, Donald, we are just above the Orion Nebula, which is right there. Okay. But I want to show you something anyway that I think is kind of cool. If you look right here, you see that red in here, this reddish area? Well, it's supposed to be the same kind of red as down here. but it's not. Why is that? It is caused by hydrogen gas that's being ionized by hot stars in this region. So how come it's not the same color red as we see here? This is kind of like the hydrogen alpha color, quite so. A little bit brighter than it should be, all right? But how come this is so very different? It's the same exact thing. The color difference is related to where it's located. This nebula that we're looking at right here is inside this dust cloud that we're seeing all around it, okay? It's inside this dust cloud, and when it's inside a dust cloud, what it means is that we're seeing the red nebula mixed with the blue scattered light from this reflection nebula, as it's called, this blue reflection nebula. And so when you add blue light to red light, unlike paint, you get a magenta color, and that's why this looks magenta, because we're adding blue and red light together. Isn't that crazy? But that's how it works, and we got to remember we're adding light. It doesn't work like paint, you know, because you add red and blue, and in the paint world, and you get a very different color than a pure magenta, don't you? You get like a purple color. And although one could say this is kind of close to a purple, it's really more of a magenta. And I'm glad we could do this in color, because you know there's many people that do this. They take black and white photos, and this is what those look like. All right, so we can look at it in black and white if we want. All right, but I prefer the color because this is a great camera. Another thing we can do is we can actually look at this the way astronomers used to look at images. They would take the inverse of them and look at them in negative, okay, like this. So this is how these used to look. This is how we would look at these things in the past. When I was getting my degree in astronomy, I had many, many charts that were all just black and white. In fact, it wasn't even this with the colors like a color negative. It was actually true black and white, you know, which is very, very interesting. So really neat. It was very nice to see that this option was available in this application. So we'll just wait for some more to come in here. Isn't that crazy though? The way that looks. Very nice. All right, let's see here. I'm going to let me start this again here, because this is it's unhappy with what I just did. Don't know why. We'll bring it right back. Okay. Might be. There we go. Nice. All right. And let me take care of you, Daryl, over here. I know you need something right here. Let me do that. So what do you think of this, guys? Isn't this crazy? It's just beautiful, isn't it? It is just beautiful.
There you are.
Yeah. Yeah. Okay. So. Okay, so this is, we're going to do one more image here. There we are, 50. That's what I want to do. So here's the thing that's magical about this. If you look right here, okay, you see that we've done 50 exposures and then stacked them together. It's the equivalent of doing a 20-minute and 50-second photo. And look what you get for it. It's just outstanding. We get a beautiful view. So we're going to save this, and I'm going to give it a name. That name appears up here. Running Man. And the Running Man Nebula is in Orion, and we're going to save it now, and you'll see in green. We're going to save it in well, you can barely see that. We're saving it in an astronomical format right there. I'll show you the name a little better. Okay, it's a FITS format, all right? But then we're going to save it exactly as seen, and that's going to be a ping file. Now, I'll show you what that's going to do for you in just a sec, because what I want to show you in particular, let me just get this up here. What that's going to do for you in particular, I'll show you after I get this down here. We need all the real estate we can get. Get ourselves some real estate. All right. Okay, so now the ping file, all right, this is what you get on the server. It'll show up here in a sec. Waiting. There you go. So this is the image that's on the file. On the ping file. Yeah, on the server, and you can download this for free. This is free. All right, and so that's what we do. We do a lot of this stuff for free. Actually, all of it for free. If you are of a mind, you can join our Patreon if you'd like, and you can actually become part of the family, part of the SkyTour family. Additionally, in the upper right, we have an Etsy store, all right, called SkyTour Shop. I would, love to have you patronize our SkyTour Shop. That would be wonderful if you wanted to. I know a lot of people in the chat have already bought stuff from us, okay, and they're very happy with the quality of what we provide. And if you just imagine this, a blanket covered with something like this, okay, a blanket for your bed. Holy cow. I mean, incredible. Okay, this has been saved, so we're going to I'll save it one more time because we can. Save exactly as seen.
If I had that on a blanket, I'd think I had an accident.
Well, thank you for that wonderful, positive message.
Like I was eating spaghetti in bed or something.
Well, thank you. That's very encouraging to anyone who wants to buy one. All right.
Oh.
Okay,
I'm
so
joking.
We're good there. And we'll go back to this here and go to 1 second here. This is now our 1 second view, the live view. All right. And now with this, we're going to go to our other aspect, the planetarium, which allows us to connect to the telescope and move to other things that we can see in here. And one of the places we're going to go is right over here. I want to check this out tonight. This is going to be a beautiful object for tonight. This is the Casper the Friendly Ghost Nebula, and we're going to head there now. I told the telescope, head there, and you're going to watch it change here. Yeehaw! Streaks. And you'll see two stars come in that look fuzzy here in just a minute. And there they are. All right. And so what we do is bring those in, center them up. When the telescope comes back, we now head over and go to the west. So the telescope moves over a little. There we go. Yeah. There's our fine adjustment. I'm going to make sure also that our telescope remains nicely focused. Always do that, because what happens, an interesting thing happens to all telescopes, and that is that when a telescope is tilted up in the air, for instance, like it is now, the mirror inside, there's a giant mirror right here, right in the back end of the telescope, right here, right? So light comes in from the top up, like from the top up here, okay? Light comes in, goes down to the bottom of the tube, and shoots back up to the top. And normally it would come back down and go out a hole in the bottom here. But for us, it goes down to the bottom, hits the mirror, and comes up to a lens, which is right here, and out to a camera, which is sitting out at the end of the telescope. You can't really see it over here, but it's about there where my pointer is. Okay? And that is where the image is being focused to, and our telescope is running 25 times faster than a normal scope of its kind. So this is a modification we chose to make to the scope so we could bring this to you quickly. And it is really, really nice. It works very well. All right, let's...
Photographically, it's working at f2.
Correct,
Instead of, that's natively an f8 telescope, isn't it?
That's correct.
Yeah.
All right, so what we're going to do now is we're going to focus right here, and we're going to do an exposure of 35 seconds. Now, being a little higher in the sky, we might not have to worry about guiding errors as much. But then again, if there's wind, that could cause a problem. So we'll see. So we are now going to start our stack up. And then once we start our stack, we will be able to we'll clear the previous. There's a lot of data in that image. Now let's go. What?
I'm sorry. Stan mentioned marathon. I assume it means a Messier marathon. I was thinking about that the other night. It's getting to be that time of year again.
That's right. Okay, let's knock down this. Let's go to enhancement, and let's or histogram rather. Let's color correct, and let's do a processing briefly just to see kind of where we're going. All right, and I can pull this back to just the beginning of our data and then back out a little bit. Here we are. So this is an example. Oh, by the way, hi Stan. I'm not doing the marathon tonight, no. It's really good to see you. Thank you for dropping by. Calabos is with me. Thank you. That's Michael and Tiffany. Mike and Tiffany, Calabos, and Tiffany Echo, you might see her in chat sometimes. Calabos is really one of our amazing volunteers for SkyTour Livestream, and he's responsible for the equipment giveaways that we do from time to time. And if you're gonna be in Indian Wells in the first weekend of June, Mike, where I'm going, I think that's Michael Tarr is it's Calabos' name, and he's giving away equipment there, but he's doing it through SkyTour Livestream. So we are his exclusive giveaway portal for equipment. We're giving away telescopes, we're giving away binoculars, and we're even going to be giving away night vision equipment from Psionics, like the Aurora Sport and so forth. It's really cool. All right.
Prime dates for the Messier Marathon this year.
Next weekend, right?
Coinciding with the new moon, March 9th through 10th, and another April 6th through 7th.
Okay. I just also have to announce that March 12th, I'm heading out to the observatory here to install the new all-sky camera. And the all-sky camera is performing very well. I've got lots of data. That's not it. Yeah, look at the beautiful detail in this, Daryl. I just love this nebula. Wow. It's got so much nice detail. You'll see this beautiful snaking stuff that it'll become much more obvious. We've got five exposures here that have been stacked, like a sandwich. And, a rule of thumb is if you say get to 20 and you see a certain amount of, noise left in your exposures, a rule of thumb is to get rid of half of that noise, you double the number of exposures. So to actually do that, you don't go to 25, you go to 40, right? That's kind of the roughly what it is. And I've proven that out time and again here. Stan says, what sky camera? And the all sky camera that I'm actually using, I'm actually using the ZWO 678MC. And I built a housing, and I'm using a GitHub all sky process or software from Thomas Jacquin. I'm also using power over Ethernet. I electrified my network cable that goes out to it, so there's only one cable going into the box. And I pick it off in the box with a splitter, power a Raspberry Pi inside the box that has this installed on it, and then use that network cable to get my live internet connection. Yeah, thanks, Tim F. Do it. JSCO 77 is with us. He was the first winner of equipment from SkyTour Livestream. Right there. He won a telescope. And the Goblin is with us too. And the Goblin won a set of binoculars from us. In fact, I think, Goblin, it was your first time you ever came to our stream. And you ended up being the winner. Wasn't that crazy? I thought that was pretty cool. Yep. Look at that. This is really pretty, man. Let's see where it wants. Yeah, let's see where it wants to go here with the processing. I'm gonna do what's called a push. By bringing these two lines closer to each other, I'm taking the mid-level data, which includes a lot of the browns and grays and some of the blues, and moving it closer to the black line. This is the black dividing line. And by doing that, it allows us to actually squeeze out some more data. It brings out more noise, but you can see now what's coming out. And then if I come over here and just punch this one, it literally throws a wild burst of data at you. It shows you what's really hidden there. So I just did it, and now you can see there's all kinds of dust here. All right, but it's also very noisy, and we don't like that. So I get rid of that, and we go back to this lower level of noise, and then I can pull this back. That is all data that's there now, and by showing it to you, I basically make it go away by moving these down, right, and changing the locations of these bars, but that data is still there. Didn't lose it. Goblin, have you used the binoculars yet?
I have a request when you have a moment.
Sure. Let me just first say, Donald Kunzer has a question, and I'm not sure what the rest of he must have asked the question further up. He says the one that rises and lowers. I'm not sure what that means.
He was talking about an adjustable stand.
Oh, I didn't find where he was saying that. Let's readjust color.
Mark, did you ever get the adjustable stand?
Oh, yeah, that's the lifting column. I have two of them in my shop here, and we're focusing now on getting a new observatory design out that won't require that. But this telescope may very well still get one of these lifting columns eventually to lift it up. The problem is, you lift it higher into the air, then the wind can move it more. The wind can move it more, and we don't want that. But so you wouldn't want to go up more than about 12 inches, maybe 14 inches, and that would actually be enough for us to, get a lot more sky with this observatory. If you notice where the walls are, you see the wall right there. That's the roof right there. That's off the observatory. You also see it over here. There's the roof there. So I actually have the roof coming off toward the east. And the reason is because toward the east, you can't see it with your eye, but that's where Phoenix is, 75 miles away. And when you look at it with your eye, it looks black. But when you look at it with a telescope, like with a camera like this, you can see a light dome, a haze. And So I said, well, look, we'll just have a telescope roll the roof off to the east because we're never going to look that way anyway, because it looks crappy that way through the telescope. But we do have very, very dark skies out there, and when I go out there on the 12th, I'm going to be heading further southeast in Arizona, and looking at another set of sites, including some virgin land that we might acquire if we can, and put a whole system on there, complete with solar panels and so forth, because this telescope does not need much power. Is it time for the X-Files? So that said, I think it's gonna be pretty cool.
My request.
Yeah, go for it.
If you have enough exposures to zoom in, I see a small red V-shaped thing to the lower right of center. About
This?
5 o'clock in the bright part of the nebula.
Not that?
No, down.
This?
Down. To the right.
Oh, this?
Yes.
Okay.
Could you zoom in on that?
Yeah, that looks like a section of emission. Let me see if I can knock out some noise.
I don't remember seeing that before.
I think it was there. This is an emission nebula here. You can see the red hydrogen emission nebula. This is a dark band which may be hiding this and this. These two things might be logically the same thing, with a dark band in the foreground blocking it, maybe. Possibly, not sure. By the way, I also want to mention that some of our SkyTour family are actually doing real science with our data. Izabela, who unfortunately is not with us right now, I think she's probably sleeping. She may show up, though. Izabela was taking our previous images and doing what I suggested that everybody do, and that was do what's called a blink comparator view. Look at one, look at the other, and see if there's any changes. And guess what? She found some. So she identified an asteroid traveling through the Pleiades, which is really cool. And I think that is a neat, a very, very neat thing that she discovered. She even identified the exact asteroid it was. So you can do this. You can do real science with our photos. You just have to be dedicated to it.
May I address Michael Hedrick?
Yeah, make sure you read the question first if he's got one.
Well, first he says, what causes the cyan color?
Okay.
Mark talked about that earlier. It's called Rayleigh scattering. It's a forward scattering of starlight in dust or gas.
Mm-hmm.
Same thing that makes the Earth sky blue. And then he says, and can two colors mix like on Earth and give a totally different color? Yes, Mark talked about that also. There are two ways. One is if you mix colors of paint, which is totally different than mixing two colors of light. If you take two colors of light, as Mark said, you mix red and blue, you'll get magenta. If you mix red and blue paint, you probably get something purple. You can get wildly different results, though, depending on what colors you mix with light versus paint. The color wheel for paint is red, yellow, and blue, and for light, it's red, blue, and green. And you can get any other color from those three.
That's right. Now, what's interesting is when we talk about stars, you know that we have red, green, and blue light coming from these stars, right? At least that's what we see in the spectrum. We'll see a green band. So how come there's no stars that are predominantly green? Why don't we see green light coming from stars? Why don't we have green stars? Ever notice that? There's a really good reason for that. And it has to do with the way radiation is emitted from objects. It's actually something called the black body spectrum. So we find that the hottest temperatures in the universe provide us with blue light. The hottest light is blue. Then as the light gets cooler, that light goes to white, and then it goes to yellow, and then to orange, and then to red. So really, yet the weird thing is, within the spectrum of all these different stars, you still can get a green signature of light in there. But it doesn't ever dominate because it's not part of the black body emission that we see. So that's why there's no green stars. It always fascinated me as a kid, because I always thought as a kid that the star you see in the eye of the swan, Cygnus the Swan, called Albireo, a beautiful star. It's a visual double star with two stars right next to each other. And I think we had a request to look at a double star tonight too, by the way. And though that particular star has a beautiful K-type star, which is orange and gorgeous, and it's next to a B-type star, which is blue. But when I was a kid looking at that star, it looked green to me because the way my eyes were receiving the light. So I tended to see things looking more green than blue. It wasn't color blindness, or maybe it was, and if it was, I grew out of it because Albireo now looks blue to me.
Yeah, it can just be a contrast effect too. If you ever get the chance to look at the star Antares, the heart of the scorpion, it's a red supergiant, kind of like Betelgeuse. Well, it has a little secondary star very close to it, and it's not easy to see. It's all people often describe it as looking green, but it's more of a contrast effect against the orange of Antares.
Yeah.
It's really more of a blue color.
Look at this. See all the detail in here, guys?
Oh.
That's really pretty. We're going to zoom in on that.
One other thing with black body radiation, the color gets bluer the hotter the object gets, but it can keep getting even hotter and hotter until the peak spectrum of emission for the black body leaves the visible light range and becomes ultraviolet and even really hot. It can be X-rays and gamma rays.
And we do see that. And that works at the other end of the spectrum, too. You can have objects that emanate only in the infrared. All right. And so that's a very interesting thing, too. So you only see them on an infrared sensor, but you won't see them with your eyes. They could be black, but emanating heat. Very fascinating stuff.
Yeah. And the James Webb Telescope, it's an infrared telescope. It sees primarily in infrared.
Actually, only in the infrared. It doesn't see anything in the visible realm. In fact, it makes the crossover for being able to see data that is shifted far into the red, and this happens because of cosmic redshift. And that is something discovered by Edwin P. Hubble. And redshift is a quality that we see with objects that are moving away from us. The farther away they are, the faster they seem to go. And this allowed us to calculate their distance. And so a galactic redshift of 2 or 3 is a distant galaxy, and there have been galaxies seen with the galactic redshift up to 10 and 11. Really fascinating stuff. And it defies logic and understanding because it suggests that the universe is actually much bigger and older than we thought. And so we're on the verge of some new cosmology here, I'm pretty sure.
Yep. I posted in our chat the other day, they have direct evidence of the neutron star at the heart of supernova 1987A now. It was seen by the Webb telescope. And in particular, They think they saw it in, I think it was the light of 5 times ionized argon that it showed up quite distinctly.
Very
And
cool.
the supernova is only 37 years old, so if we can really see the neutron star, then that's the youngest neutron star we've ever seen.
That's actually right. Yeah. Yeah.
I have a request after Casper.
Okay. But look at that. That is a beautiful region right there. That is really something.
I'm probably confusing this. This is not the one with the true void, is it?
No, that's the iris.
Yeah, okay. The dark cloud is reminding me.
Yeah. But you see all this little filamentary stuff here? Let's see if we can punch out some of that and kind of show it to you. You can see a little bit of it there. And let's see if by color correcting that might make it a little more obvious. Oh yeah, look at that. Looks like this is a ball covered with blue dirt and it's falling off. Really interesting. So you ask yourself, what's the dynamics going on in this region? What's moving all this dust? It looks like it's in motion. Where's it going? Where'd it come from? This is all part of understanding galactic motion and the orbits of dust clouds, stars around the center of our galaxy. Our sun has gone around the center of the galaxy approximately 20 times since it was formed. 4.6 billion years ago. So that's around 230 million years in orbit or so. Yeah. Kim Libby, hey, how are you? Nice to see you. I saw Kim on Night Dreams Radio last night. They had a guest on there, and I called in, asked a question. Night Dreams Radio with Gary Anderson is a syndicated show, and Gary has me come on every 2 weeks to discuss astronomy and the latest developments, and that's where I think Kim heard of me. It was from there. It's nice to see you here, Kim. I hope you subscribe, Kim, and hang out with us, and look at the stuff you see. And by the way, when we save this, as I'm about to right now, one of the things I want to say is that you can download these images for yourself less than 30 seconds after we take them. So you should, you might want to consider doing that. Casper the Friendly Ghost. This is known as M78 to Measure 78. So I'll just say M78 along with that. Okay. Look at all the satellites. Zing, zing, zing. Can't get away from them.
Hoopy, what describes the creation of dust in deep space? Basically, it's like red supergiants. When they cool off enough, it allows molecules of dust to form. And like silicon, carbon, stuff like that.
Yeah, the physics, though, Ufi, is the physics of accretion, okay, and mutual gravitational attraction. Out in deep space, I know this looks like a really turbulent region full of crap and everything floating around, but if you were there, it would look like everything else to you, because once you're in the middle of this, you don't see it as focused and concentrated looking. It's all distended, and the brightness is way less. If you were, let's pretend that this star and this star were the same distance. If you were here, you might not even see a blue glow here. It might actually kind of look like a slightly lighter, but it'd be across much of your sky, and you wouldn't see any of this dust at all unless you did deep exposures, and even then, you might not catch it. And how do I know that? Well, because when you look at the Pleiades, you know how the Pleiades has dust around it that you see when we take that photo, right? And when you take pictures of dust from a long distance away, it's very obvious, like this, like the Pleiades stars. But when you're in the middle of it, you may not even see it. Case in point, the Pleiades again. It turns out that the sun and the whole solar system, including Alpha Centauri and other nearby stars, might actually be in that same cloud of dust that the Pleiades show when we take a photograph of them. We might be in that cloud. Isn't that crazy? Why would we not know that? Because it's around us. We're in it. We're embedded in it. We can't see the forest because of the trees. And that's exactly the kind of thing that we might encounter if we ended up going, say, to the Casper, the Friendly Ghost Nebula here, brought out a little bit more for you. So that's the thing, this stuff, this is light years in length, many light years in length, okay? So it's 4 light years to Alpha Centauri, okay, this system. Well, there's many light years, more than 4 light years in this length right here. I could actually calculate the length. I wrote a little program to do it, and I got a Photoshop thing, an action it's called, which allows me to do all that. It's kind of cool, and it shows you, the nature of these objects in 2 dimensions. You can only measure across and down. You don't know how far into the page they go or how far out. So you can only get the smallest distance they might be from each other, kind of a thing. But it's still pretty cool. So,
Another way to put what Mark was saying is you're still looking at a pretty darn good vacuum when you see that dust. It's just that the scale is so great. You're seeing many light years deep of dust stacking up, making it visible. It's still a vacuum.
Yeah. Libby, thank you. Kim Libby, thank you for that comment. I'm glad you're subscribed along with your husband. Thank you so much for doing that. This is something we do out of passion and love for science, as you can tell. And you listen to me on Gary's show, Night Dreams Radio. Our radio show on Sunday nights, 8 to 10, is SkyTour Radio. This is SkyTour live stream. All things astronomy all the time. I mean, it's really one of the most incredible opportunities that we're been afforded. And to have a telescope 2,500 miles away from where I'm sitting right now, and to be able to operate it like this, looking at the night sky and showing people all over the world astronomy, this was a dream, okay, an absolute dream. I never knew it was possible until I started looking into it, and then I realized I have a lot to learn. So I had to learn electronics. I had to learn some other science, of signal processing, all that stuff to figure out the details. And I'm really not the sharpest knife in the drawer, okay, but I am able to get it done. Astronomers are usually pretty sharp guys, so I tend to think maybe I'm kind of that smart compared to some of the others that are way much more smarter than I am. But bottom line is, it's just really enjoyable to be able to share all this with you. Look at this beautiful wings of dark stuff. I actually never saw these here, Daryl, that much. I think we always focused down here, but look at that.
Uh-huh.
Yeah. Oh, this is beautiful. All right, we're gonna save this here. This is 44 shots taken. 45. That's good. All right. There is our save right here. That's the astronomical file format, and then we're going to save it exactly as seen. Now, if you go to skytourlive.org, this up here, all right, okay, this, sorry, that was a mistake. There we go. Let me just pull this back here. Am I doing good here? We got it? No, there we go. All right. Don't know what happened there. Okay, but anyway. If you look up here, skytourlive.org right here, you go here. That's the portal to everything you see here. You have access to, from there, you have access to SkyTour live stream on YouTube. Okay. You have access to our wonderful Etsy store, which is right there, SkyTour shop. You have access to our Patreon. If you'd like to join our Patreon, boy, we could certainly use the help. So feel free to join our Patreon and help us out. We would really be appreciative of that. It's something that, like I said, the Patreon, we started it, a year and a half ago. So, we get members here and there who want to join up. But, if you think about it, this is out in the middle of the desert. So how are we getting the internet? We're getting it from those pesky satellites you see in our image. We're getting it from Starlink. So, Starlink's, quite an expensive prospect, depending on the quality you want. We have just the middle of the road, and that's still $120 a month. So we depend on people helping us out in the Patreon to keep us going. So now, Kim Libby asks, what makes the dark lines? Is it different dust makeup, shadow of some sort? That's a really excellent question, Kim. This dust you see here, this is actually just a denser, that's what makes this darker, is it's a denser clot of dust, all right? And these denser clots of dust are actually what make the dust look more opaque to you, right? This is somewhat opaque, but you can still see the stars through it, right? This is thicker. It's harder to see the stars through it. Those that show through it, like right here, it's kind of hard for the light to poke through here, because it's a denser dust. When I say dense, if you were there, like I pointed out before, if you're right in the middle of this dust, you'd still see the universe around you like this, because the dust particles are actually quite far apart. How far apart? Okay, well, in air, molecules in the air, okay, there's about 10 to the 30th molecules in the air, in a cubic centimeter of air. It's like 10 to the 30th atoms, all right? In dust like this, right, the denser parts of the dust, you might have 30,000 atoms per cubic centimeter. But from a long distance away, they look opaque, right? Just like clouds in the sky. When you see clouds in the sky, they look solid, right? The puffy clouds look like cotton balls. But you get in a plane, as you get closer, they get wispier and wispier, and then you're in them, and whoa, we're in the cloud now. You didn't even see the edge almost coming, And you really see that when you'd see that if you're actually in the cockpit looking out the nose of the plane. That's when you would actually see that the cloud coming towards you gets more tenuous. All right, so that's how this works. Same prospect. Okay, we did 51. We're going to save this now. All right, and we'll save it exactly as seen. And again, go to skytourlive.org, and as you scroll down, you'll see a number of things. One of the things you'll see is I want to see cool pictures. Take me to cool pictures. And there's instructions there on our server. You get to the server, and you can see tonight's pictures live, full resolution as they are here, and then take them down. Now, if you're a Patreon subscriber, for the upper level Patreons, we do the final processing to show even more detail in here, okay? And that final processing we make available to you for no cost if you're a Patreon member. So I guess there's a cost, right? But if you're a subscriber, to get an idea of what I'm talking about, the kind of detail you can see, if you look at my SkyTour livestream Facebook page tonight or Mark D'Antonio Facebook page, I just put up a post showing a mosaic. You also get mosaics as a Patreon member, where I actually went to different spots in the sky and took long exposures of each section, and then made a private made a giant image that I fully processed with incredible detail. I showed it to Daryl earlier, and he saw it. So these are really nice images that would be made available to you as a Patreon subscriber. So that's something that to consider. If you want to get some of this data, you can get the free ones. These guys with no problem. These are free to take down, but they look about 10 times better than this when we're done with them. You know? So that said, let's close out Measure 78 here. And I've saved it, so I think I did that one more time. I'll do it with 55 shots. Did you say you had another
suggestion?
Yeah, I was going to say, did you say you had another idea for what you wanted to see?
Yeah, I'll leave it up to you if you want to do it. You're very close to the boogeyman.
I knew you were going to say that, and I was thinking about it too. It is right on the other side of where we are. All right, let's... we should do that. We should do the boogeyman.
I might mention you talked a day or two ago about looking at the Spaghetti Nebula too.
And the dolphin head too.
Yeah. Somebody asked earlier about looking at the bubble. I know it's in Cassiopeia. I don't know if it's too far down or what.
Let's go take a look. Oh, hello, I'm in it. Hello, that was silly of me. Let's go see. All right, Bubble Nebula. The Bubble Nebula is a really fascinating location. Yeah, that's pretty far down there right now. There's the horizon. And that means the telescope will be pointing way out the back there, you know, that way. That way. So we might not see it. But, because that's where the bubble is. There's the north. There's the pole.
Right between Cassiopeia and Cepheus.
Yeah, they're way down there. And, you know, astronomers generally don't tend to look at objects that are way, way out there in the horizon, because those objects would tend to be quite quite fuzzy, because you're looking through more atmosphere, and that's a problem, you know. So Leo is coming up, Leo the lion, and Leo is heralding, you know, galaxy season, which is starting soon. So we'll be looking at lots of galaxies. I haven't taken pictures of them. By the way, for those that may know this, may have forgotten, this particular telescope has a camera that I changed out. The camera we used to use was what's called a ZWO 294 MC Pro. It wasn't tuned to this focal length, so we weren't getting the best results. But we didn't know any better until I started doing calculations. When I did calculations, I realized we need a different telescope camera. And so we got a different telescope camera that actually matches perfectly. So we get results that are considered, they're actually labeled as exceptional for this particular telescope combination. Our focal length is 503 millimeters. And again, that's 25 times faster than what the telescope was before at f8. No, you don't multiply 500 times 25, okay? That's not how that works. But the focal length was up around 2,500 millimeters or so native, and we actually got it down to 500, and that makes it photographically 25 times faster. Well, I'll tell you what, since we're here, let's go and do what you suggested. And to do that, what I'm going to do is first turn on, I know the name, but I just want to turn it on so we can show folks. I'm going to turn on the Sharpless catalog, LBN, and LDN catalogs. And that's good. And look at all the stuff we got. All right. So, is it right there? LDN 1622.
Yep.
This is known as the Boogeyman. And where is it? There's Orion right there. Can you see Orion?
You can barely see that dim red curved line there
Oh, yeah.
just left of Orion. That's
Right
called
here.
Barnard's Loop.
Hmm.
We just looked at Casper, which is just inside Barnard's Loop, and now if we go to the Boogeyman LDN 1622, it's just on the outside of Barnard's Loop.
This is Barnard's Loop, remnant of an ancient supernova. Again, littering the cosmos with all kinds of wonderful periodic table elements from which you are made. I think that's pretty cool. All right, let's go to LDN 1620. LDN stands for Lynn's Dark Nebula. LYNDS. And there's an LBN too, Lynn's Bright Nebula. And Lynn catalog has several, many entries. The LBN catalog and LDN. All right. So now what we'll do is we're going to head to the east a little bit, because this right here is where we want to be. Just flop it over like that. Okay. And I think we come... Is it here? Let me just do a 20-second shot here just to see what we got here. There we go. A quick 20-second shot. And this will be a placement shot for us. I'll leave this up so you can see our yellow bar over there moving over. There we go. All right. I think this is... Let me see where this is. It might be that bottom nebula there. That didn't help me. Okay, well, let me just come back here. Come in here. Center up. Okay, and 56 around. Let me give our field here. Let's put our field in view here. That's our field of view. And that's probably 56 Orion, right? So I see it right there. So we're you see this. Oh, we got those two over there.
I think you wanted to go the other east.
I mean this way. You want this to be over there?
Yeah.
Yeah.
I mean, that's the double star, and then the one closer to the Boogeyman was the single bright star.
Mm-hmm. Oh, duh. I gotta go back to the 1 second. Yeah, that's why. Okay. All right. So where are we here? Let's see where we are. So that was the double star. Right there. 59 Orion. Is that right? Yeah. And then we got to move a little further to the west. And then we should be okay. There we go. Okay. All right. And that's the single star associated with the Boogeyman. All right. So we come in here. And now we're here. As you can see, we gotta I have to resync everything, which I will do. All right, so what we're going to do now is we're going to put this guy down here. So this
Well,
is
he's
going to
wanted if 56 or Orianus, the right one there on the right now, if that's what's actually illuminating the nebulosity around the boogeyman.
to see the spectral type. Let's go this way.
Maybe, maybe not.
Yeah, I have to see what the spectral type is. So right now the boogeyman is right here. All right, and I'll show you. You can kind of see it now. But what I'm going to do is just come back in here for a sec. All right, we are now tracking. And let's get this. All right, so that's where we are. Right there. And let's do this. All right. So I'm syncing with that. So now that's kind of close. So what I'll do now is I'm going to look at this one more time. Yeah, okay. That looks like that'll work. All right. Now let's actually do a exposure. And this will be another 35-second exposure. 35,000 milliseconds. We are guiding. You can see here that our numbers are changing. All right. And we shall now go and do our guide. All right. And that's our previous one we looked at, the Casper, the Friendly Ghost Nebula. This will be up on the server. It's up there now. And we're going to bring in the new one. You can see the progress bar going in, down, going up down there. Okay. We're waiting for a Starlink satellite. So the first exposure is probably done already.
Looks like your frame at the bottom right's frozen.
I just said that. Waiting for a Starlink satellite.
Oh.
Yeah. All right, so what I'll do is take us out and bring us back in. Here we go. And our frame is now here. There we go. There's the boogeyman right there in all its glory. Oh, look at that. We have a tumbling satellite up there. Very nice. Very nice indeed. All right, let me take care of this here with you. Okay, there you go. And all right, here we go. All right, so you can see this is starting to come in very nicely, and there is a beautiful little reflection nebula down here, an emission nebula, a soft emission here. This star is red, which means lower temperatures, so I don't suspect that it's ionizing this hydrogen gas to make it glow. Another star is responsible for that. It could be any star in this area. It could be a star buried inside here, as a matter of fact.
Yeah,
Sometimes it is.
It.
So let's color correct this now. There we go. And let's do a quick process. All right. There we go. That's looking pretty already. Let's take this up. Temperature out in the desert is inching upwards now. It's going to be, during the day, it's up to 80 or so Fahrenheit. At night, it drops down pretty chilly, but Cosmic Ray has put up some information about Lynn's Dark Nebula number 1622, which is what this is. Also known colloquially as the Boogeyman Nebula. I'll call it actually LDN, which is what it's really called, 1622. Wonderful. As time goes on, we have 6 done here. You'll notice that our frames, we have 7 frames now. Number of frames rejected on windy nights, we'll see that number climb, and that would correspond to a red bar here, which we don't see. In fact, we're at 8.68 at the highest, so I can drop us down to just above that. So this means we'll maintain the roundness of the stars at this particular point. Because if it's round at the highest number, then dropping to the highest number as a threshold is perfect. If we get a wind burst, it'll pop above that and ruin the shot, and we won't let it, because we will just ignore photos that are not of the right quality. It guarantees that we get perfect shots every time. Here we go. So, when you look at it through a telescope, for instance, and you look at an object like this, one of the things you'll notice right away is that it doesn't look anything like you see in a photograph. Now, the reason for that might be obvious to some, but not so obvious to others. The reason is that if you look at an object in a telescope, you're looking at it through a little tiny telescope, which is your eye, 1 power or so. And the size of the pupil is the size of your telescope. This telescope is a 10-inch diameter telescope that we're winging around there. And unlike your eye, which accumulates light, it takes in the light and then it releases most of that light. It passes it through to the brain processes it and says, oh, look, a car coming toward me. Okay? The evolutionary benefit is that you see things as they're happening. You see things moment to moment. You can hunt. You can capture game because you have the ability to see things the moment they happen. We're doing a 35-second exposure here. We don't see what happens for 35 seconds, and then we see what happened in the previous 35 seconds. So camera sensors have the unique ability to be able to accumulate data. That's what this is doing. Your eye, on the other hand, can't accumulate that data that way. It's very, very different. So we're instantaneous image gatherers. The camera is a accumulated image gatherer. And there's talk about the eye and how it works and whether there is some latent image that is kept behind. And that's somewhat true. But in comparison to a telescope, there's no comparison. You'll never see this with your eye unless you have a sensor that you're looking at it with, as we're doing right now.
Mark, Michael Hedrick has a question of you. Sounds like he's talking about interferometry.
How Keck combines light and... can you talk about how Keck is a telescope on Mauna Kea, combines light and how radio telescopes combine signals?
From multiple sources.
Yeah, to answer that question, Michael, let's also talk about what that does for us by taking multiple sources. Let's say we had 5 other telescopes in the world, all looking at this nebula right now. Could we combine that data? Yes. They're so far away that no matter where we look at it from the Earth, it's going to be the exact same orientation and configuration. Now, yes, if you're different curve of the Earth, you got to rotate the image to get it exactly the right way. If you're down south, it's going to be upside down, so you're going to have to flip it the other way. Okay, but we can do all that later. So you get all the data, and what you do is you combine it and you stack them all together. All right. Now we do it with optical imagery. We do it by stacking them together. So we've combined right now 14 images. It says so right there. 14 images right here. Okay, and we've stacked them all together. Now, if we had 14 different radio telescopes, then we could stack the images. But what's important when we're stacking from different telescopes around the world is to stack in the order they're received and to stack them in a way where they're all synchronized with each other. All right? We can't just willy-nilly stack them, all right, because we're actually doing live observations, so they have to be stacked and synchronized with each other. That's where the term interferometry comes from, because we're actually trying to stack things in the order that we receive them. I mean, that's sort of kind of what's happening there. The VLA down in New Mexico, I was there. The Very Large Array is doing that with 23 or so different radio dishes that they can move on a track. The farther away they go, the different resolution they get. Okay, the closer they are together, the different the resolution is there. And so they take these things and they move them around. So they combine all of that, but because they're all operating at the same time, they have to be synchronized with each other, and all the data has to be brought in just the right measure. Otherwise, it'll be kind of a mess. I can't explain it any further without having to demonstrate it, but I can't. I don't have a way of demonstrating that here.
The time, what kind of time period are you talking? It's less than fractions of a second, correct?
Yeah,
I mean,
and
you're probably talking like thousandths of a second.
Yeah, and that synchronization has to occur. And I give you an example: the Event Horizon Telescope. This was a supremely good example of how this works, because we had observations being brought in from all over the world, from many different radio telescopes. And they were somewhere up north, somewhere down south, somewhere on the equator. Effectively, what they are is they're setting up basically a pretend telescope that's 8,000 miles in diameter, which is the diameter of the Earth. And as they observe this one object in the center of the Virgo galaxy called Messier 87, they were able to image the black hole at the center of this galaxy, 44 million light years away. Now, the black hole was very large. Let's be fair. It was actually about 5 to 6 times the size of our entire solar system. That's a huge black hole. That's why they're called supermassive black holes. And this particular black hole was imaged by these telescopes. But because the black hole is moving so quickly, right, meaning not through the sky, but in and of itself, the rotation rate of this black hole was very high. So we had to be very careful. They had to be very careful, even more so when the black hole at the center of our galaxy. They had to be very careful with making sure they get all the signals processed and synchronized together, all right, so that you could get an adequate rendering of this exact point in time, and then this exact point in time, and then this exact point in time. That's something that these many radio telescopes had to synchronize. That was the hardest part. That's the hardest part, And thank you for actually answering Kim Libby. I was going to answer it, but I'm glad you got to it. Kim Libby asked, is the Andromeda Galaxy have any other names? And it does, Messier 31. if you look at the Andromeda Galaxy, you notice there's two other galaxies. That the smaller one that's closer to the center of that galaxy is called Messier 32. And then there's one a little farther away called Messier 110. It's a little more elongated. Turns out Messier 110 is actually a little further away, or a little closer. I'm not sure which way. It's just further into the page or out of the page. I think it's further away from us. But it's a satellite galaxy to Messier 31. The Andromeda Galaxy. Look at the beauty here. This is nice now.
Michael, there's also a different thing that goes on. It's called multispectral imaging, I guess. I don't know that they really need to time it like interferometry, but if they'll look at an object with optical and various non-optical telescopes, radio, infrared, ultraviolet, you name it, they can take the same image at different wavelengths, different frequencies, and build an image from that. And it can show you a whole lot more of what's going on in and around an object than, say, single frequencies or, red, green, blue, whatever. Can show you. Like they can combine images from Hubble, from Webb, from the Chandra X-ray telescope, and learn useful information from it. Plus, it makes pretty pictures.
Yeah. I just went full screen, guys, just to show you a little bit more. This you notice this little knot of dark nebula right here, and this one, and this. These are separate knots, and they're, of course, isolated in the space. This one is several light years from this one, and so forth. Well, this knot of dust right here, interesting about this knot of dust, it's most likely a gravitationally condensing cloud, self-gravitationally condensing. If there's nothing else around this, then there's nothing stopping it from being attracted to itself with all the many particles that are in there. So what's going on in the middle of this dust cloud is probably this gravitational contraction. And this gravitational contraction could lead to hydrogen gas that's in there being compressed really immensely in the center of this dust cloud, which could lead to one or more stars forming in there. The dust itself is being compressed, which could lead to more molecules and more elements that are available to a young star system that may form within this dark cloud. I've said this before, and in my Facebook post, which I hope you'll read tonight, if you haven't already, I talk about life began in the dark. And so it's in these dark nebulae where life itself begins, all right? These are the chemical cauldrons. And I have to be careful about cauldrons implies hot. They could be hot, like this dust, this gas and dust in here. This gas is hot. It's being hit and excited by ultraviolet energy from hot stars somewhere in the local neighborhood here. And so it's causing the hydrogen to emit light because the electron jumps off, it's ionized, then it recombines with the atom and gives off light when it gives up energy. And that light is characteristically red, like we see here. So, but in the dark, this dark massive cloud, if it gets dense enough, then the ultraviolet light, which is damaging to carbon-based life, right? Mars is sterile because carbon-based life can't survive at this point on the surface because the ultraviolet radiation is penetrating all the way to the soil and going a couple inches into the soil, rendering it sterile. Okay, but in a dark cloud like this, this dark cloud, the denser it gets, the more ultraviolet light it can stop. Right? It's not that hard to stop ultraviolet light, but a good atmosphere and a good dark cloud can do it. And so what happens is inside these dark clouds, you get these little oases of potential safety zones within these dark clouds that may allow for life to spring forth on a planet that might have formed inside these dark clouds. That's how we started. We started within a dark cloud. And our sun was born and illuminated the dark cloud. It was probably a nebula, much like this one down here, around our star for a period of time until the star itself blew that away with its radiation pressure. All right. So that happened and could be happening here. So what you're looking at here, you could be looking at a brand new set of star systems that might be forming out there, or a cluster of stars that may eventually spring forth from this region. This is just a snapshot in time to us. But the universe has time aplenty. So over time, a lot can happen here. You know. Hey, Calabos, I believe you are going back to work tomorrow, are you not? Let me know that. And do not worry, it's so good to see you. I hope you have a good night, and I'm sure that we'll see you again soon. Calabos, he works at SpaceX, and he has work tomorrow, so this is good. So, that said, I'm hoping that we can do a equipment giveaway sometime soon. It won't be tonight, but that's all right. I have a feeling you would just really enjoy some of the objects we check out. And you know what's nice is you get to learn about what these things are, you know, and then see what's over your head. This is something right now you'd never ever be able to see this in your normal day-to-day life. You'll never see this unless you see a photograph on a show. Well, you're seeing a photograph, and this is the show. Okay, but the thing is, you're seeing it live. This is live. It's happening right now. And that's the thing about astronomy that I could just never get over, and that was that even though the universe is a great big time machine, we're seeing this as it was a few hundred years ago, okay? Maybe 300 to 500 years ago. It's a lot closer to us, potentially, than some of the other nebula we look at. But that said, even though we're seeing it at some time in its past, we're seeing it live right now to us. The light has reached us. Now, if we didn't look at this, that light would come and go. No one might see it. So this nebula is made available to us because of that.
May I point out the boogeyman?
Yes, let me
Why
come
they
back out
call
of
it the
here.
boogeyman?
Yeah, sure, go ahead.
Okay, where Mark's arrow is pointing right now, that is the boogeyman. He's a ghost-like figure. He's lying on his left side, which is down for us. His head is on the right. His feet are to the lower left from there. His left arm is down. His right arm is pointing to the upper left toward the other dark clouds. If you can see that figure, he's sort of ghostly looking, and that's the boogeyman.
He's a Dementor. He's a Harry Potter Dementor, right? Isn't that what it's like?
I don't know what a Dementor is.
What?
I have never seen a Harry Potter movie.
Okay. Let me just color correct so we can actually see this a little better.
Not my cup of tea.
Mine either. But I watched it because I had kids. Okay.
Speaking of, my tea is cold.
Well, go get some new tea.
In a few minutes, I will.
All right.
Too
right.
late for more tea.
So there you see now, that's some of, like I said, what we do here. And, you know, I got to say, and I've said this, Daryl knows this, there's literally nothing else like this out there. I have never seen anyone doing live, universe live in real time like we're doing. I think that's why it's so popular now at these conferences. When I do conferences all over the world, and I'm doing one out in Palm Springs area, Indian Wells, and that'll be the beginning of June. But back in April, I'll be in Arkansas, and I asked them if they want me to do this. They do, but they don't have reliable internet there. I need internet. But in Palm Springs, I'll be doing this live. And then I'll be doing it live in Roswell, New Mexico in July at a conference there. And I have a traveling SkyTour live stream set up that I take with me. It can fit in a backpack. I set it up, pull it out, bam. Go stream the universe. Just incredible. You know? Fantasy says, if I'm free that weekend, I'll attend. You're talking about the Indian Wells Contact in the Desert conference out in Palm Springs area? Oh, here we go. X-Files. I was supposed to put a log on the fire 2 hours ago, so I'm sure it's out. I'll have to go put it on. Temperature's cold right now. Oh, fantastic. Fantasy. I'd like to meet you, too. I haven't met you before. Good to see you. And maybe I'll have some of my books there if you want to pick up The Populated Universe. And actually, the things that you're learning here, guys, and I know I say learning, but you know what? Why not, right? You open up your minds, you learn about things. The Populated Universe is the story of us. It tells you about where we came from. It talks about the universe, talks about carbon-based life in the universe. You learn many of the things I tell you here, I've talked about in the book, and it's really kind of cool. I mean, there's people in the chat that may have read the book already, and they could tell you if it's worth buying or not. And I'm open to honest criticism, so I don't have a problem. It's been out for several years now. But the version that's up on Amazon is the latest version because I update the editions constantly as things change, as I learn new stuff. So I just upload the latest and greatest. And that becomes the book that gets sent out. Pretty cool. Hey, Linda Judd, how are you? Has anyone made a prediction of what dark matter is? Actually, that's a fascinating question. I have to say, Linda, dark matter seems to be, notice I say seems to be, what causes galactic rotation to do what it does. Now, when you look at our solar system and you look at the planets orbiting the sun, Mercury goes around the sun in 88 days. Pluto takes over 200 years to go around the sun, right? Closer to 300. But what's happening? It's going a lot slower in its orbit than Mercury is, obviously. It's a lot further away. So objects further away orbit slower. Objects closer to the center of gravity in a solar system or star system will go faster. That's physics. And that's something that we thought was a mainstay that we could depend on. So you'll be surprised to hear that when we studied galaxies, we look at galaxies with all their stars. Well, the stars are also going around the galaxy's center. So we figured the stars at the center would go whipping around really fast, and the stars on the outside would go around slowly, right? Yet when you look at the galaxy and you look at the spiral arms are sometimes kind of loose, right? And not very well defined. Sometimes they're really tight and sometimes they're not. So wait a minute. If that's an indicator of galaxy rotation, then something's wrong. And in fact, they are an indicator of galaxy rotation. But what we look at is how fast are the stars moving around these galactic centers. And it turns out that when we look at the outer reaches of a galaxy like our own, the stars are moving at a certain speed. And when we look in the middle of the galaxy, the stars are moving at a certain speed. And at the center of the galaxy, they're moving at a certain speed. We would expect there to be a vast difference between the stars close to the center, that we would think would move fast, to the stars in the middle, to the stars moving outside, which would be moving a lot slower. Well, guess what we see? We see that the rotation curve, that is the speed at which the inner, middle, and outer stars are moving, is not as different as we would expect it to be. The outer stars are moving at quite a clip, and the inner stars are also moving a little bit faster. That's called differential rotation. The innermost stars are moving a little bit faster than the outermost stars, but not enough. Not enough to account for what we see. What we see is that the stars on the outside are actually moving at a rate that they shouldn't be moving at. They are moving faster than they should be moving. Okay? So how is that possible? The only way it's possible is if there's some other unseen matter which has gravity that is also tugging on them and surrounding them and allowing them to move almost like a disk, a solid disk. It's not a solid disk. It's not moving at the same rate as a solid disk. Okay? But it's almost like a disk. So why could it look like that? Why would it move like that? It can move like that if something called dark matter exists. Now, dark matter isn't matter we just can't see with our eyes. It's more than that, okay? Certainly we don't see it with normal sensors. In fact, we don't see it really at all. We only infer its presence. It's different. It's not like what we call baryonic matter, matter made of the atoms that we know about that are like in our periodic table. There's something more going on, and that's what dark matter is. It's that something more, that little extra thing that we can't identify yet. No one actually has a good definition for dark matter at this point. So I know that's a long answer, but I really believe in being thorough. So hopefully that helps you. I guess I just did tell you that we don't know what dark matter is, didn't I? Now you have dark energy too. Dark energy is the reason why the universe is accelerating as it's expanding. At least that's what we think. Daryl doesn't so much believe in dark energy, but then again, he never saw Harry Potter and doesn't even know what a Dementor is. So hey. So I want to say hello. Okay, we got, who's this now? The Woo and the Pooj. Okay, how you doing, man? Nice to see you. And Blindy Mitchie's back. Good to see you again. Nice to see you, man. He's doing the Vulcan sign there. I saw that. Yeah. You know when Spock does that? You know where that actually came from? Do you know that in Hebrew and in the Jewish faith, that's actually a symbol that's used in the Jewish faith? I didn't know that. That's where they got it for the show. He just did that kind of unconsciously one time. And they said, hey, I like that. And so it became something that everybody does and everybody knows. But they usually don't know where it came from. This is nice. We've got 48 frames stacked here. We're going to stop here in just a minute. Michael Hedrick says, Mark, is there any chance that space-time is warped and gives us the illusion that things are moving at different speeds than they really are? Okay, let me say that again. Is there a chance that space-time is warped such that it gives us the illusion that things are moving at different speeds than they truly are? I have to say this. I've always wondered, and Daryl, maybe you have too, is cosmological redshift real or not? Have you thought about that? Well, Daryl's there somewhere. Anyway, my thought process on it is that we're looking with the James Webb telescope at galaxies, and we're noticing things with galaxies that really make us wonder whether the universe is the age it is, or whether it's older than we realize. There's a lot of information that might indicate we're looking at a much older universe than normal, than what we believe in. So what I'm going to do is I'm going to bring this back. Put that back up there. And let's bring back the telescope here. Good. All right. you get your tea?
I dumped the tea. It's too late for tea. I grabbed some water.
Oh, okay. So this is coming out pretty nice, Daryl.
Uh-huh.
Yeah. All right. Well, we'll save it. We've got 52 shots here. That's more than enough to make a beautiful Boogeyman Nebula. Do you have any other suggestions? Should we just continue over to Rosette?
Sure.
Okay.
You mentioned the spaghetti nebula the other night.
I did. And it's
I don't
pretty
know if
much overhead right now.
Okay.
It might just be overhead. I can look.
I posted that APOD in our chat the other day. It was a really beautiful picture of the spaghetti.
I saw it.
And I looked it up on Stellarium. On my Stellarium, I don't know if it would look the same on yours or not, but the actual, like where the crosshairs were, where they said the spaghetti nebula was,
Yeah.
is actually just at the very center of what looked like a huge cloud of nebulosity.
Yeah.
And I think the APOD said it was like 3 degrees on the side or something.
Yeah, it's big. Look at this.
Just
Here's the
that
field
big
of view.
tumbled area there.
Yeah. Now, I was looking the other night when I did a test. I looked at this segment myself, and it looked really interesting, but it is pretty faint. And we would have to do like 1 minute exposures for like 50 frames or more to get anything reasonable. So if we start the night out, if we start the night out and do that, that's what we'll look at. Now, if you notice right now, okay, look where we're looking right now. If we hit, this is our equatorial coordinates. If we turn those off and turn on these coordinates, you'll notice that it's pretty close to zenith, directly overhead. Okay, so here is Orion, right, and there's the Spaghetti Nebula. All right, and it's actually kind of, if we look here, it's sort of, I'll take off the zenith coordinates. You can see now it's pretty high in the sky here. It's actually at least 60 degrees in the sky. Let me see here, the altitude. 62. Yeah, so, but it's still, we should start tonight with that, you know?
I figured, and if it's 3 degrees on the side, you'd have to do like a 9-shot mosaic or more probably to catch it all.
Yeah, and I would plan on doing that, but I don't want to make everybody sit through that, although I would love to make everybody sit through that, but they don't want to. I can tell you that they want to see cool stuff, right? So here's what I'm thinking. Now, right down here also, in Canis Major, is the most beautiful nebula that you could see here, and I think this is another a Wolf-Rayet star. Is that the Dolphin Head? Is that a Wolf-Rayet or supernova? Do you remember?
I want to say Wolf-Rayet.
I thought it might be, but I'm not sure.
Let me look it up. I forget.
All right. So what I'm going to do now, since
Dolphin Head?
Yeah. I'm going to take us over to the Rosette Nebula, and we'll just work on that for a bit. This is a beautiful, beautiful cluster. You look where the telescope's pointing, you can see where it's going.
Yes, it's a Wolf-Rayet star.
Yeah.
EZ Canis Majoris.
Yeah. So this is the cluster, and this cluster is in a nebula, what's called a stellar nursery. I will confirm that our telescope is staying focused. Now the temperature out in the building is 13 Celsius right now, 13.62 Celsius actually. and I want to make sure that our focus stays the same. I do have a what's called a temperature compensation coefficient, where you have a value and it automatically changes the focus depending on the temperature. I found that to be kind of reliable, but I've also found sometimes it throws everything off. So I don't want to actually depend on it, and I haven't been. I've been just refocusing as needed. So I'm going to zoom in now and see if we need to refocus. We may or may not. It depends on how the telescope has been behaving. It looks like we might benefit from a refocus. So what I'll do is I will move it slightly out of focus, and the stars will get a little larger, and then I will refocus like I did earlier. By the way, when you refocus or when you defocus the stars, you can see their color more obviously. Like stars that are blue show as blue, stars that are red are really red. And you might not see that with a point source because it's really, really, really bright in the sensor. Okay, so we'll focus this.
Michael H. is just full of questions tonight.
He's got great questions.
Yeah, well, I'll point it to you because he's asking you, Mark. One question I have is, there a known upcoming event that recurs every 1,000 years or more?
Is there a known upcoming? I'd have to look at solar cycles to see. There might be a deep cycle in the sun. But there's certain comets that come back every so often. Halley's Comet, for instance, is 76 years. And comets, every time they pass the sun, they evaporate a little more. So Halley's Comet will eventually be a non-comet. There are no Oumuamuas that you can predict. Those are extraterrestrial visitors to our solar system. So I don't know of any 1,000-year cycles. Do you, Daryl?
As you said, some long period comets. 1,000 years in particular, who knows? I mean, there are some very long period comets out there. Some we've had just in the last couple of years that they've predicted to have, orbits thousands of years long.
Yeah.
If you're talking on something cosmic scale, though, not that I know of.
Mark D. Truth Searcher, what's going on, man? And you said, okay, I bit. And Puck Elf, how's it going, man? If you guys that are new here, do subscribe because, we bring you the universe live in real time, and there's really nobody else doing it. And we're looking now at a cluster. We're focusing the telescope right now. You'll see this little shape here. You'll see a line appear here momentarily as we it says the focuser scan completed, so I think that it missed this because of the nature of how it came about. Let me just going this way. I might have gone the wrong way with it. Ha! That's okay. Let's bring it in. All right, we'll take it out here. Okay. All right, let's do it again. Somehow we missed that. Oh, actually, let me just reset. Here we go. All right, so we're gonna just refocus here, like I said, and get this to focus up our system for us. And what it does is it builds a focus curve, and at the bottom of that focus curve, it's going to put a line that is the actual direct focus. It doesn't mean it's where the focus stops to test it. It means it's going to build a curve and then find the minimum of this curve. Remember your geometry, you found minima of curves? Well, this is doing that as well. It's going to find the minima of the focus curve, and that minimum is going to be some point where the curve is, at the vertex of this curve, of the focus parabola. So we've gone into focus and then out of focus, and then a line should appear right about here, which, there it is. And that's our absolute focus point. So now we can just say best focus, and it'll line up on that line right there. I talked to the author of this software, and he put in this process, I think, in part because of what I mentioned about it. Because, you know, as an astronomer, I think he values my opinion. Okay, so there we go. And so now I'll zoom back out here and show you this overall image. This is the cluster. Now, what happens with a star cluster? It's really cool, and I'll start a exposure so you can see it. I'll do 30 seconds, which is 30,000 milliseconds. As a star cluster forms inside of a cloud of gas, what happens is the star cluster itself, when the stars form, they're very young, they're very hot, they're very powerful, very energetic. They give off a lot of radiation. That radiation pushes stuff. When you go out into the sun, you feel the radiation hitting your face. You might feel wind too, but you're feeling the radiation hitting your face. As minuscule as that is, you're feeling radiation pressure, the pressure of the impact of the stellar radiation hitting your face. It's actually something that is measurable, and it's something that is part of the reason that this cluster looks the way it does. And you'll see that in just a minute. You kind of saw a little sneak preview there as that first image popped in. I didn't quite get it in time to catch it, but it's coming. The next one's coming right now. And you'll see stellar energy in practice. You'll see what it does. So if we look at this object here, look at this beautiful cluster. Let me get it into the shape that shows you just what we want to see. Okay, this is called the Rosette Nebula. Okay, and if you look at the Rosette Nebula, you'll notice something really interesting. You'll see that in the middle here, where the stars are that formed, there's a hole. See that hole? Well, that hole, in astronomy, we call it a cavity. That cavity was formed by these hot young stars and the radiation pushing out in all directions. So inside this amorphous cloud, when a star cluster formed in there, this particular set of stars then blew out and pushed away all the other dust and gas that was in here. And it formed, in part, some of the shapes you see out here. Okay, this cluster of stars is only a few billion years old. I don't know the exact date, but I think they can. I think they have a value on that. I'll have to see. Let me just do some processing here to kind of soften this up to show you a little bit better what we're looking at. And what I'll do now is I will go up.
How old is the cluster?
I think it's only a few million years old. If you look at, you can probably find that on.
Yeah, the cluster is 2244, isn't it?
Yeah.
I
think it's a few million years old. Vince Giglio, how you doing? Good to see you. Isabella's with us. Hey, Izabela. Izabela, I always call her a superstar. She's the one of the people that does amazing processing. Izabela, I touted you earlier, and for those just arriving, I wanted to mention that Izabela has taken our data and done some real science with it. She discovered an asteroid floating through the Pleiades that we captured on a date, and then using other Pleiades photos was able to confirm it. And then she even was able to identify the exact asteroid it was. So everybody, show your love, congratulate that girl. She did a beautiful job. Well done, Izabela.
Less than 5 million years.
Yeah. So it's young, and so that's why we see the cluster in this particular condition. All right, let me. This is worth popping this down and going full screen with. Let's pull this out for now, and let's just bring us up close and personal. Yeah, look at that. Yeah, look at that. Hey, Fairy May, how are you? I see a lot of new faces. Make sure you subscribe, guys. It's free. If you want, these pictures are made available to you, by the way. And they're all at SkyTourLive.org up here. All right. So if you actually end up going to SkyTourLive.org right here, you can see the pictures. We have on our SkyTourLive.org. You scroll down, you'll see Take Me to Cool Pictures, and you can go there and check them out. Then if you want, you can go to our Etsy store, SkyTour Shop, and you can check out photos like this one right here that are on everything from sneakers to bedspreads to mouse pads, and get some phenomenal imagery that we highly process, and then enjoy it. I think we have people here in the chat who've purchased some of these things. And you don't have to take my word for it. Just ask them what they think, because they got the products. They see what they are. Again, SkyTour Shop on Etsy if you want, and SkyTourLive.org, which is the portal into everything SkyTour. From there, you can go to our radio show on Sunday nights, which is SkyTour Radio. You can go to SkyTour Livestream, which is the thing you're in now. You could go to our SkyTour Shop. You can go to our SkyTour Patreon and maybe join our Patreon. We would so enjoy having you as part of our Patreon. Please consider supporting us and become a member. That's something we can always appreciate and do always appreciate. And the nice thing is, for Patreon members above a certain level, you'll get pictures like this. These are the free ones. You can download these now. Everybody can. But what we do is we highly process these into masterpieces. And one of the people that does that is right here in the chat, putting out the Patreon link. That's Izabela. She's one of our top-notch processors. I'm another one that does the processing of these things. And we show you the universe like never seen before, to be honest. And as I said, no one else is doing this out there. I really honestly don't understand why. I just don't. I mean, I do understand why. This is not that easy to do. This is a process. It takes an awful lot of effort and a lot of people to come together. SkyTour Livestream is a 501c3 organization. We can certainly use your help for sure if you got a way to subscribe to us from as little as $3 a month. And we have people that are literally way more than that per month. We got $100 and $200 a month subscribers. Not many of them. Let's be clear. I think only one of each. But we don't have a whole lot of Patreon supporters right now. I think we may have 10, 12, maybe 13 of them. So I don't know. It's possible. So Daryl, as the comic relief to the stream, would you like to add anything?
No.
Okay, that was funny. So, and then thank you, Izabela, putting up that for the store, and of course, thank you, Daryl, for doing that as well, because you do that a lot as well.
I'll do it right now. There is the link directly to the server, folks, where tonight's images are landing.
Yeah, I better put this up there now that we're off the.
I should probably learn to put up whatever SkyTour Live or whatever it's called.
SkyTourLive.org?
Yeah.
Oh, that's okay.
I know where this is on my bookmarks, my favorites.
Yeah. Well, I mean, it's listed in the description for our stream. It's always on our streams. People can go look at it right there. It's always listed up above. So, yeah. Hey, Papa Tom. Thank you for coming, and good night to you. Yeah. And
Oops,
Puck,
I missed Pop Tom.
yeah, he just said good night. Hey, Puck Elf says, I still have my high school level little hobby optical telescope put away someplace. You know what? I had a 2.4 inch refractor that I actually used plumbing pipes to make a mount for. And I had that for years. And I let a guy borrow it when I used to work, for another company. And I never got it back. And you know what? It's okay. I don't even know whatever happened to it. It was my very first telescope. I just thought it was the coolest thing. And Mark D. Truth Searcher says, staring up at the stars is something that really puts things into perspective sometimes. Yeah, no doubt. And I just like the idea of looking at something like this, which is thousands of light years away, and which is generating this cavity from the stars and their powerful radiation. And it's just literally pushing the gas and dust away and forming the shapes you see in here. Good night, Kim Libby. Thank you so much for coming. It was a pleasure to talk to you yesterday in the Night Dreams radio chat. Why are you lost?
I don't know. Maybe because I snuck off without announcing I was leaving earlier. I can't seem to find my place in chat.
Oh, that's what you mean. Well,
Or people are talking about things, I have no idea what they're talking about.
oh, okay. Yeah, okay, I see what you mean. Because you had to go get your tea done or whatever, and yeah, understood. Oh, this is so pretty, though.
It is a nice image.
Yeah, let's see if we can do a little processing on it that might help. That softens
there
up
at
some of the
about
noise. Yeah.
9:30. I thought it was especially standing out nicely tonight.
This here?
No, farther up.
Oh, here?
That right there, yes.
Oh, yeah. Let's zoom in on that. We've captured 20 images so far of this region. As we zoom in, you'll notice there's a tremendous set of convolutions, but I want to point out something, and Daryl, you know I do this every time we look at the rosette, is these little tiny black dots. You see those? Those aren't on your screen, guys. Those are actually in this nebula. Now, in real life, and there's one here too, in real life, these little globules, all right, that you see all throughout this nebula could be new stars that are about to form or new star systems. Okay, now inside these dark globules, which are called Bok globules, B-O-K. Bart J. Bok was an American not American, but astronomer that I had the pleasure of having for classes when I was getting my degree in astronomy. And Bart J. Bok was the discoverer of these globules and the nature of them and what they mean. What they are gravitationally collapsing dust globs out in space. And as they get smaller and smaller and smaller, they get denser and denser. And at the very center, the temperature gets hotter and hotter. And if there's enough hydrogen gas collapsing with it, then what could happen at the center of these globules is you'll get a star to form in there. And at the same time, you're going to get an accretion disk, that is a disk of material forming around that young protostar, as it's called. And that material can end up clumping, and that material then can form a set of planets around these stars that may form. And Bok globules are among the most important things to study in these clusters, And the Rosette Nebula, that many light years away, this globule is very large relative. It's going to be many solar systems in size, you know, many solar systems in size, to put it into perspective. And this is this tenuous dust here. This is shaped very likely by this set of stars here that are using powerful stellar winds to shape the cavity that they created when they formed, and they're pushing this dust around. And in areas where the dust is dense, they can't push it as well, like right here. So this material is staying, right? Meanwhile, this stuff back here, all right, is sort of tenuous and is being pushed away and pushed back. Here's a dense area right there. That dense area is being pushed, but it's actually protecting, because it's so dense, it's protecting the stuff behind it. So that stuff is actually safe. And this stuff that's denser up here is not as easy to push. This is why in nebulae like this, we see things like this down here. Look at this long tendril right here, and it stops with this knot of material right there. Let's zoom in on that. Okay. This is called a stalk. S-T-A-L-K. There's a stalk. There's one right here. There's one right here. And Daryl has told you this before. It looks like the Eagle Nebula that we see in the summertime. Messier 16, the Eagle Nebula.
Took the words out of my mouth.
Sorry.
It's the very same process, like the pillars of creation.
Yep.
The pressure from the big bright stars in the cluster there in the center is actually shaping those pillars.
Right.
It's blowing the matter radially away from them, and where the matter is dense enough, it's sort of protecting the matter behind them.
In fact, that's right. The stalk is the result of these ultra-dense areas here. If these weren't dense, then this would have been worn down. But because they're dense, like Daryl's saying, the material behind them is protected. It's in the lee side. And so we get this amazing stalk. And we see this in a lot of nebulae. Deborah, we've seen this in maybe 100 different nebulae we've looked at in the past.
Oh, yeah.
And
everybody's heard of the pillars of creation.
Yeah.
And Messier 16, the Eagle Nebula.
Mm-hmm.
But they're all similar processes going on.
That's right.
And you see them, they're like the ones at the upper right there, they're pointing back toward the center of the star cluster.
Yeah, like this one right here. Okay, we got this one. We got this one. Okay, this one. So the denser heads of these things are harder to erode away by hot, bright starlight. And you'll also notice tails. Like here is one with a tail on it. Look at that. Okay, has a tail on it. These tails are also very obvious in star clusters. Here's another Bach globule, and another, and another, and another. I mean, they're everywhere. Here's another. And again, notice a stalk pointing at the cluster. All right? Another stalk pointing at the cluster right here, right here. Okay, another one right there. They're ever present. This one is quite pronounced. So remember what I said last time, if you were with us when I mentioned this. When you look at the power of the stellar radiation, it's not like it's searing the life out of everything. It's not. It's more of a gentle ultraviolet and stellar radiation that they're giving off. It doesn't have to be sterilizing, but in the young hot star cases like this, you've got many young stars. And by the way, I did a study on the Rosette, just so you know, and each of these stars is minimally about 8 light years from the other. Okay, in 3 dimensions. So it's about 8 light years. These are about 8 light years apart in here. Okay, and so from this point of view, and that's looking at them flat. But remember, there's 3 dimensions, so they're actually some are closer to you, some are farther from you. So from this area here, where this stalk is, all right, this could be being carved by these stars and even these stars up here. but they might be further away from you. So they're carving from two different angles or multiple different angles. Fascinating stuff. So this nebula has always been one of my favorites because it shows everything that young star clusters can do in the galaxy. They can create oxygen glows. They can create hydrogen glows. They can create globules. They can create eroding stalks. They can create reflection nebulae, okay, like we see right down here, okay. They can create all kinds of effects that we see in the Rosette Nebula. Here is one of those nebulae that shows most of them. So I hope you're enjoying this one. I'm going to color correct because the background's a little too blue.
I thought Bart Bach was still alive. He died over 40 years ago.
Yeah. He just aged me very well.
So, I mean, surely, you know, there have been high resolution astrophotos of the Rosette, for instance, for a long time now. And I'm sure other people saw those dark globules.
Uh-huh.
It was Bach that figured out what and why they are what they are.
Yeah. That's right. Mark Truth Searcher asks, where are you getting this screen from? You mean this screen that you're seeing here? This telescope is the same as that telescope. This telescope is, I'm in Connecticut. The telescope's out in the Arizona desert. I installed it out there with the help of Marianne Robb and Tara Diulis, who are part of SkyTour Livestream's 501c3 not-for-profit company. And we basically did this with all the money that we had. We didn't have donors. We basically did this on the shoestring that we had. My job was to figure out how to get what you see 2,500 miles away in the desert to be shipped all the way out to Connecticut, where I am, and elsewhere in the world, wherever I might be. And my job was to make that image available to you. So this product here is called SharpCap, and SharpCap, written by a guy named Robin. Really, really excellent application for what we do. And we combine multiple applications to do what we do. I actually wrote software for Arduinos, which are microprocessors, microcontrollers, for those of you that know what those are. And basically, it's how I tell hardware what to do. For instance, this roof rolls on and off. How do you make it roll on and off? I put a relay inside a ordinary garage door opener, and I retrofitted into the existing hardware. And by sending a certain signal to this circuit board, it'll put the roof on and off and roll the roof on and off. The telescope is being controlled through drivers, and the power to the telescope is controlled by me. I have a system that I wrote to actually do all that control. So that kind of thing, it took about maybe a year and a half to figure out, 2 years. And then I implemented it on a small scale. I had an observatory on the front lawn here, a real dome on the front lawn of my home here in Terryville, Connecticut. And everybody knew the dome in Terryville, Connecticut. They would drive by, take pictures. Look at that thing. It looks like a giant minion on the front lawn because it looks just like Stuart the Minion. So on Halloween, I dressed it up like Stuart the Minion. And let me tell you, we had all kinds of people say, hey, get pictures of that thing. You know, you look just great. So that observatory I outgrew. And so I sold it to a guy on Long Island, down in New York. And we're going to do something a little different now in the front yard. We're going to be using and putting in a solar telescope here. We're going to be looking at the sun during the day, and we're going to look at the stars at night. So I won't be getting any sleep. You know, I've used that solar telescope many times in the past. In fact, I taught science at a facility that actually had a solar telescope built in, and I spent months at the eyepieces of this telescope. That was long before we could actually get digital photographs of these things. Well, now we can, and so it's really amazing. So I'm going to have a solar telescope out here on the front lawn, and it'll be in an enclosure that's automated. I'll be able to run it from anywhere in the world, and I'm in Arizona a lot. I'll be there, like I said, March 12th through 19th or 21st, installing a new all-sky camera. And that new all-sky camera is going to be something that's really, I would say, a really good camera compared to what I have out there now. I have an all-sky camera now. The all-sky camera that I have out there now is really not very good, and it was the best we had at the time, without a doubt. But now I'm going to actually replace it with something far better. And this camera, as I mentioned, is is a ZWO camera, a 678 MC camera, and I built it into a all-sky camera mount and use a Raspberry Pi with free software that you can get, which I'll be happy to share all that with anybody if they want to learn. So, what did I miss in the chat here, Daryl?
Puck may have been referring to you. He was asking about sterilizing radiation. What was meant by that, if you said sterilizing radiation?
Yeah. Sterilizing radiation is high frequency radiation, like ultraviolet radiation, X-ray radiation. X-ray radiation can damage your DNA and literally kill you, obviously. Sterilizing radiation is the UV. Generally, that we're talking about. In fact, the surface of Mars is sterile because of UV radiation from the sun, ultraviolet radiation, reaching the surface of Mars. Now, Mars used to have a heavy atmosphere, for instance, but a cataclysm of some kind drove that atmosphere off, or the magnetic field decline on Mars may have allowed the radiation to come in because that magnetic field no longer acted as a shield to high energy particles coming into the atmosphere like our Earth has. So
and the UV is liberating hydrogen from water on Mars too. It's dissociating the molecules.
Yeah, if you have an H2O, as Daryl's pointing out,
Yeah, and the hydrogen gets freed and it floats up and leaves Mars. Might be what you were referring to, Puck.
Yeah. Park says, so organic compounds forming from hydrogen bonds. Yeah, absolutely. Okay, let's consider water. Okay, 2 hydrogen atoms, 1 oxygen atom. Okay, the bond is easy to break, and so when you have high energy ultraviolet radiation coming in, it can disrupt the bonds between the hydrogen and the oxygen. Okay, and the hydrogen and the hydrogen. So what will happen is the oxygen will get freed up, all right, by this high energy radiation. And then the hydrogen, now liberated, can float up into the atmosphere because it's lower gravity and escape to space. The oxygen, on the other hand, is a little heavier. That could stay down near the surface, and when it gets near the surface, it may bond with something down there. Oxygen loves to oxidize. It loves to bond with things. So we'll find the oxygen bonding with all manner of things, usually iron compounds. And we know that 2 iron atoms and three oxygen atoms can form together Fe2O3, which is what? Rust. And so Mars is covered with rust-colored dust, and that's why Mars is red. That's why people say, "Oh, the red planet." It's because it rusted, because that oxygen was removed from that. Yeah. So, Cosmic Ray says he's using a Raspberry Pi high-quality camera, 12.3 megapixel Sony, and 4 sensor on my 120-degree Skycam. Okay, so you went with the Raspberry Pi camera then. Yeah. Yeah, it's all good. Yep. Yeah, and you have to get the right lens for the all-sky camera. Not you, Ray, but me. Because right now I have a 170-degree field, so you can see all the way to the eastern horizon, all the way to the western horizon. But north and south are cut off a little bit. You want that circle. I don't have it right now, and I'm not going to put it in yet. I'm going to actually consider that for a next visit to the observatory. I'm going to be out there in May. And Mark Truth Searcher says, isn't the moon beginning to turn red also? Actually, there's some truth to that, because what happens is when the unfiltered energy from the sun strikes the lunar soil, the high energy radiation that strikes the lunar soil and asteroids, for instance, as well, and does so for a good several billion years, you can get a reddish color that is generated by the interaction with the radiation and the soil. Now, the moon doesn't have as much, for instance, as some of these asteroids we've seen. It's thought that Oumuamua was actually a deep red, so it's possible that was floating around for quite a lot longer, and it encountered more intense ultraviolet radiation than our moon has here around the Earth. Remember, the moon is not subjected to a constant bath of this. It's on the far side, the side away from the sun. It's not feeling any of that until that side gets around, because it's actually the same face is facing us as it goes around the Earth. So only for half of its cycle does it actually have sunlight on its surface. Okay, so for all the time that it gets sunlight on its surface, well, that could contribute to a radiation reddening that will occur. So there is soils on the moon that are very different colors. There's white soil, there's orange soil, there's some red soil. And of course there's some gray regolith. Regolith is the word for soil on the moon. So it's pretty interesting, and it has really interesting properties. It's made of a lot of sharp shards of material from countless billions upon billions of meteorite strikes. And in an airless void where there's no erosion, when that meteorite strikes and the stuff cools, it tends to cool in sharp pieces of what is almost like glass. So
I saw a good video on YouTube this morning talking about lunar soil.
Yeah.
And how dangerous it is.
Yeah.
It's poisonous. It's toxic. It'll carve up your lungs if you breathe it.
Yeah.
Smells like burnt gunpowder.
Yeah, or burnt steak. I heard burnt steak too.
If we ever stay on the moon, I mean, they're going to have protocols to probably showers or something to knock the dust off thoroughly, so people aren't, inhaling it or eating it or breathing it.
Yeah, they could end up with silicosis and things.
Yeah.
Those sharp shards. It's interesting because I remember I had dinner with Alan Bean, the astronaut, and Captain Bean and I were sitting there, and we were talking about the moon, and he was talking about the lunar soil, and he was saying that we had to really be careful when we're walking on the moon, because as we shuffled our feet on the moon, what we didn't realize until Harrison Schmitt discovered it was that that moon dust was cutting through our moon suits.
Yeah.
And I think it was Harrison Schmidt. I think. Forget, but Schmidt noticed that he was getting suited up to go out on the last moonwalk. It would have been his last, all right, because his moon suit was cut all the way past the insulation on his ankle, and from the dust, it was like, wow, look at this. Now, these guys weren't wearing masks in the lunar module, so they had dust in there. It got everywhere. I remember I was doing a show on Discovery Channel for, I think, NASA's Unexplained Files. Now I'm on A&E with History, which is owned by A&E, for The Proof Is Out There. But on NASA's Unexplained Files, they asked me, can you recreate lunar dust, recreate moon dust with all the proper properties? And I said, well, maybe. Let me look into it. So I did, and I said, if I do this right, then if you breathe it, you'll die. Okay, you sure you want all that? And they're like, well, wait, can you do it without the dying part? I said, okay, I can simulate the static properties of lunar dust. I can simulate the compacting properties, like the footprint, okay, that Armstrong left, the famous footprint, right, or Aldrin, whichever one. And I said, but I'm not gonna simulate the glass, microglass, okay, because that's simply deadly, and I won't do that. And they said, okay. So I did it, and I actually have it in my shop right now. I've got several gallons of it that I created for the show, and it was to simulate how footprints work on the moon and how that dust actually gets everywhere. And when we filmed that, they filmed it here. I was dusting my shop for weeks afterwards because everything got coated. Even though we're being very careful not to set it up in the air, it got everywhere. Okay, so even the simulated moon dust got everywhere. It's very, very lightweight. That's the thing, and there were larger particles in there that I had, and if you sifted it, like in a sifter, okay, the large particles stay behind and the dust falls down slowly. That's just what it was like on the moon. So and that small stuff combined with the big stuff is what compacted it. So you got a footprint. When you stepped and made a footprint, it made a perfect casting, so to speak, of the footprint, because that small stuff was like a binder with the large stuff. Really eye-opening, to do that. It was really something,
I used to work in mining a long time ago.
Mm-hmm.
I worked in the largest underground mine in North America.
Yeah, you did, didn't you?
And dust like that, silicosis was a problem.
Yeah.
They gave everybody respirators, and they recycled them constantly. They had processes for washing them, sterilizing them, and putting new filters on them and all that. And we all wore the headlamps like you see in old movies and stuff. And some guys took their health so seriously that they put on the respirators before they ever went underground, entered the mine, and they didn't take them off unless they absolutely had to. They would go in the lunchroom and take them off while they ate, but otherwise a lot of guys would wear them non-stop until they left the mine again.
That's dangerous too, though.
Some people wouldn't bother until they saw dust floating in the beams of their headlamps. And they say if you waited until you saw the dust, it was too late.
Yeah. You know what's funny, Daryl, is the
pretty nasty stuff.
Yeah. These guys that wore the masks all the time, they thought they're being safe. As it's turned out, people that wear masks for a long time, they're actually putting pressure on the diaphragm muscle and on the lungs, and it can actually cause a heart attack in some people, because of the pressure that you're inducing 24/7 or 8 hours a day or 10 hours a day. So they actually recommend not wearing a respirator. Like I wear respirators when I work in my shop, and they say do it on and off, take it off often, and get to clean air, which I do. In fact, over my head here, I've got in my office, my bunker, I've got a system that cleans the air every 3 minutes. I mean, I've got SLA rapid prototypers here. I've got 4 computer systems in here. So I've got a lot of things here that can't get dust in them. You know what I mean? So, so if I'm wearing a respirator in this room, then it means there's something really bad in the air that I needed to get rid of, sooner. But which mine was that? Up in Leadville?
Near Leadville, yes.
Yeah.
Called the Climax Mine.
Oh, I remember that mine.
Yeah, it on top of Fremont Pass, 11,265 or 70 feet, something like that. The molybdenum mine. The mine opened during the First World War, when they discovered that molybdenum could be used in alloying steel.
Yep.
To make cannon barrels for the war effort.
Wow.
And been open ever since. 3,000 people worked there when I was there.
Wow.
It was a huge operation. It was like a whole city underground.
I believe it, like an aircraft carrier.
Yeah.
It's got to be self-sufficient.
Much bigger. It was like 170 miles of tunnels underground.
Wow.
It was huge.
Don't get lost.
Anyway.
Wow.
Gosh, you're up to 70 some odd images now.
I know, and see, I remember when he talked about, like, if you want to really cut down the noise, if we did like 35 images, if you want to cut the noise in half from that, you go to 70. So while we're talking, I let it go. And now I'm going to go to 75 and stop. And look at this. Look at the quality of this stock system here. This is going to be one beautiful image when we're done. So I'll let this come back. I'll bring it back in. Dock up here. There we go.
Should make a nice image.
Yeah. Hoping so. Let's see what this wants to be. Yeah, see? When these don't move that much, you know you're actually pretty close to a good image. Okay, there's 75, so we're going to save it here. Save it exactly as seen. And this will be available to you with all this detail for free in about 35 seconds up on SkyTourLive.org in the Take Me to Cool Pictures location. Remember, guys, if you have just joined us for the first time, please do consider subscribing. It's all free. If you have a mind to, after you've been with us for a while, and if you really like what we do, consider $3 a month, $5 a month, whatever, for a subscription. Love to have you. And we're going to say goodnight to the Rosette Nebula now. Wow, that came out really pretty, I have to say. Really pretty. Look at that. Wow. Let's see what the color correction wants to do. Very nice. Now see, this is a one-shot color camera. Many cameras actually just do black and white. So this could have been the image we saw. Not nearly as impressive, because when it's in color, you can actually see the subtle gradations between some of the features, like in here. This is something you would lose. You'd lose this amazing feature here. You'd lose this subtlety in here. So I like what we got here. This is great. All right, one last save, and then we're done. Really cool. All right. Well, folks, I am thinking that we have done a really good set of images for tonight. And again, we're gonna call it quits for tonight. But I do hope that you'll join us next time. The next time, what we'll do is we'll actually look at some supernova remnants and some Wolf-Rayet stars. Supernovae, obviously, stars that had core collapse. Supernovas with the core collapse, and boom, the star blows up. And then the Wolf-Rayet stars, which are fairly young stars that actually have such energetic stellar winds like the ones we saw that carved a cavity here, okay? But far more energetic than that by a million times sometimes, that they actually literally push their outer atmospheres off, leaving only their cores. And they leave a nebula around that active core, which is still doing fusion, but it's literally at a frenetic pace. It's amazing. But those stars are very massive and will always end their lives as a supernova. So I'll show you those next time. In this sky, we have Thor's helmet, we have the Dolphin Head Nebula, and we have several others that are Wolf-Rayet related. So enjoy that the next time we get together. So until then, I hope you guys had a great time tonight. To the newcomers, thank you so much for coming. Make sure you subscribe. Go to SkyTourLive.org because this is where it's at. We're literally the only ones doing this on the web. There's no one else that's doing these nightly sky tours like this, and showing you the universe live in real time. Well, there's people doing photographic stuff, but look, you got astronomers who show you what's going on, tell you all about the objects, and then teach you all about these things. So if you're not careful, you'll learn something. So do please consider supporting us. Oh, Izabela just said that. Thank you. Support the channel. Anyways, great to see you guys, and thanks for coming. For those that are new, hi Jessica, I see you there. Thank you for coming, and we'll talk to you very soon. So have a good night, everybody.
Good night, everybody.
Good night, everybody.